Welcome back to the UGDBF Tutorial Series. Today is XFLR Part 2, where we're going to use XFLR5 for stability estimation of a DBF scale aircraft. So today we're going to have a look at how we can define aircraft models within XFLR5 to do a stability analysis. We'll look at what kinds of stability analyses are available. Usually these are fixed velocity or fixed trim. And then we'll have a look at the loci plots that they produce and what those mean to us engineers in terms of how an aircraft's going to handle. And then obviously, because we're engineers, we enjoy exporting plots to make pretty MATLAB and Octave plots for our reports. So we'll look at how we might do that, especially on older versions of XFLR5 using the log file. Obviously, typing in each individual locus point by hand is not ideal and not a very good use of engineer time. And finally, we'll have a look at once we've interpreted what those plots show us, the ways in which we might be able to address some of the underlying behaviors and problems that we have on a particular aircraft. So in terms of the workflow, this is carrying on from episode 6. So at this stage, we'll assume that the airfoils are loaded in, they've been analysed correctly, we have good data across a good range of Reynolds and across a good range of angles of attack. And so for all that stuff, that's covered in part 6. Then we're going to kick that right off and define our aircraft model, and then we're going to go ahead, define a stability analysis, run it, and then we're going to have a look more interpretation of that analysis, the loci plots, exporting them, and how we should feed that information back into the design process. So assuming that you already have your data, we're going to go ahead and I'm going to go ahead and load up some data from a previous DBF year for UGDBF aircraft, and we're going to have a look at defining how we go about defining a I have my polars good. We're going to look at defining an aircraft with the intention of getting a stability analysis put together. So this is actually a finalized aircraft. If I should check the masses, yep, this is for a particular case. And we actually have very different use cases for different aircraft geometries, where we're looking at different scenarios for how the aircraft performs and how stable it is in various flight configurations. So let's go ahead and define a new aircraft. Just define a new plane. So this will be the demo plane. So we're going to have a look when we get our main wing together. In this case, we're probably going to set a 1.6 meter span. Let's go with a 0.32 to 0.24. That's not quite what I wanted. 0.24. Something, yeah, something. Should be a bit chunky, hey. Don't know, we'll go insert a couple of sections in here. Let's do a 0.32 midsection. We'll taper that down to 0.24. We'll go down again to 0.16 on the tips. Yep, we're going to bump that. Some like so our middle section will be offset is 0 at Y position. We get a 20 centimeter inboard section that is unchanged. We're going to need we're going to assume we have a wing spar running down the leading edge. So we're going to have an untapered leading edge and a tapered trailing edge. And we are going to set that very, that's quite a nasty progression, hey. Something like that, I suppose. And we'll go to 0.16 here. Maybe a bit aggressive. Let's go to 0.24, not 0.24 on both sections. Right, and then we're going to go ahead and set our aerofoils into place. Okay. Now then, so if you followed on from episode 6, what you'll end up with is a model like this. And this wing, this is a fine wing. Let me just remove the things we haven't actually asked for yet. Elevate from fin. And this is fine. You'll notice that with masses turned on, we currently have a central gravity of 0 kilograms, and it's right at the origin because there is no mass. Now, a lot of people I've seen try to do this get very excited, and they get to this step, and stability analysis does nothing for them. And the reason for this is that they haven't defined their control surfaces. Unfortunately, control surfaces are defined at the direct foil design stage. And the way you would define a control surface is if you were to take your original aerofoil, in this case an S1210, I am going to assume this is what the S1210 looks like. It's probably been modified in some way. The way you would do this is you would set the flap parameters. So you can either have a leading edge flap or a trailing edge flap, and you would basically set where it is as well as where the hinge position is. and the default angle. Now when you do this, it'll ask you to save it as a different aerofoil. Now, despite there being no changes in this aerofoil, I've already done this with mod 1, as you'll see by the... Oh, apparently I have not done it for mod 1. Interesting. We actually have to run that. We're actually going to have to do this in real time. So nothing seems to change. That's fine. We will need to reanalyze this aerofoil, since you could make changes to it, and it would be none the wiser. I'm going to go ahead and put in my normal parameters in here. Okay, update polar view. We'll go ahead and clear all polars real quick so we can see what's going on. Can I hide all polars? Current polar, show only associated no. Okay, current foil, show only associated right. Multi-thread batch analysis. Yeah, I can't park you. Okay, once it's open, fine. We'll go from -15 to 30 in 0.5s. Actually, I'll do 0.1 so I can do this all live to tape. Save myself some time. And we'll go 10k to 200k in 10s. Come on, chop chop. Okay, and then we'll run 200k to 1,000,000. And we'll do that in 50k. Ram, wham, wham, wham. These should all finish pretty much at once, I think. Yep. And then we're going to need to run 1,000,000 to 5 million, and we'll run that in 250Ks. Right. So we'll just reanalyze this aerofoil. Nothing actually really changes. The S1210 actually has some issues above 20 degrees where it's stalled and you get a lot of turbulent flow, which XFLR is really not good at dealing with. This is fine. You actually see the turbulent flow behaves at a shorter angle of attack with higher rounds numbers. Which is what we would expect. Everything here looks reasonably in order. And there is a key change now. When we go ahead and edit this wing, where you have a control surface, you actually need to define the aerofoil as the one with the flap. And you'll see here it actually draws in where the control surface is. It's now, one would say, why would you not have the aerofoil let's just use the mod 2 everywhere? And the reason for it is you typically do not have control surfaces along the entire edge of your aerofoil. So that's why you actually need both. It's a bit of a faff, but that's how XFLR goes, and it's free and it's doing your work for you, so not much you can really complain about. So I'm going to go ahead and set up some panels real quick. Yeah, 5, blah, blah, blah. Cool. This is terribly ugly, so we're going to have a wee look at going to probably uniform and U. I want to go probably, yeah, uniform inboard and then cosine on the tips. Yeah, okay, that looks not too terrible. It's mostly a case of trying to minimize the discontinuities between the aspect ratio of the panels. So what you don't want, for example, is really thin panels next to really big panels. This is not fantastic, but on the whole, the progression isn't terrible. I'm doing this quite quickly. If you were doing this for real, you'd probably go to the 4,000 to 5,000 number of VLM panels and 3D panels sort of region. So then we're going to define a quick elevator, which I will do with the NACA 0012. Again, this is absolutely evil. We're going to have to set that to cosine, and we're going to have to go for more panels. Okay, something like this. Probably want something like that. Like that. Yeah, it's very minimal taper. Yeah, that's fine. And we will add a fin on the aircraft, which again will need to be a symmetrical aerofoil. So let's go NACA 0012. X panels, a bit more. We want to go probably cosine. Yep. White panels, yeah, cosine, fine. Okay, so at this point, we have a basic aircraft model. We do, however, need to move our fin so that it comes in line with the leading edge of our tail. And the way to do that is very simple. You would just match up the offset. So basically this sets the origin point of each wing. So let me just show you what that does exactly with regards to the main wing. You'll see here the main wing currently goes through the origin. If we were to make it, say, go through at -0.1, it would move the wing 10 centimeters forward. So this is how you're going to start defining geometry. And it's especially important to note these offsets when you start fixing the behaviors of an aircraft. So that you know, hey, this is my geometry before, and I need to apply a fix of this much, and you would save it as a model, compare two models, and see if that improves your stability. But for now, we have an aircraft defined, we have the wing, and that's not enough. If we did this at the moment, we have no masses. So one way to do things very quickly is to define the mass of each wing, elevator, and flap, and this will assume that they are fully uniform. Let's go with 2-4 on there, and we're going to have a very light, well, not very light fin, but comparatively light fin. So if we do input these masses, what you'll see is the COG, center of gravity, actually updates. In this case, that makes sense. The tail's quite heavy. It's 0.34 kilos, and it's quite far behind the main wing. Let's actually add a wee bit 1 degree of angle of attack on the wing. And we also need to probably define, for example, a battery mass. Let's put in 0.8 kilos. That's going to be about 10 centimeters forwards of the origin. And that's going to be our battery. For example, we can also come in here and go ahead and define our motor and ESC, which we mounted even further forwards than that. So let's go to minus 1.15. ESC motor. This is mostly just keep tabs of what you're putting in. So once you've done that, what we'll find is that our center of gravity is closer to what we would expect. Now, we are pretty much ready to run an analysis. And actually, one thing that's worth pointing out is I have not added a control surface version of a foil on the tail, mainly because when we define our analysis for a stability analysis, let me just save so it doesn't crash. If I define not an analysis, we can actually define an analysis that we did for a wing to get the overall performance characteristics of a plane, but that will not take into account the trim state of the aircraft. So obviously, if we are making negative lift on the tail to keep the nose level, we're actually going to lose some performance to that. So a stability analysis actually does keep that in mind when we do things. You can actually set our flight conditions, our beta and our slip angles if you need. We do want viscous analysis defined already, that's fine. Clicking platform control parameters. This is the important one. So the way that the analysis is going to work is what it's going to do is it's going to, for a range of parameters, set the wing tilt, elevator tilt, and flap angles proportional to that parameter, and we'll run through that range of parameters. Then what it will try and do is it will try and trim the aircraft out. It'll find a speed at which the aircraft flies reasonably level, or at least makes as much lift as it is heavy. And then we can look at what we do is we'll come in and have a look at the behavior and see whether it's whether it's actually flying, or whether it's in a trim state that ends up with a unscheduled rapid disassembly at the end of the whole thing. So in this case, the wing tilt on our aircraft is fixed, so we can't affect this. We can, however, say that the, for example, elevator tilt will be just 1, so just proportional to the parameters that we run it in. So this is the parameter that it's going to use. We're going to start at, for example, minus 5 degrees elevator tilt. We're going to end at 5 degrees, and we're going to go up in half-degree steps. And we can run this through. And this is the step that usually takes quite a long time. You'll see that the matrices for these things, when it starts to calculate them, get quite big. In this case, I've done it quickly. I've got very few panels. This is quite quick. And you actually see it starts putting out these eigenvalues for longitudinal and lateral modes. So we'll wait for this to finish up. Yeah, a bunch of cannot be interpolated for at least these particular CLs, that's fine. Not all aircraft states are trimmable. Some aircraft states are highly unstable and result in an aircraft no longer flying. Stall conditions, for example, and the like. So we're actually almost done here. 3.5 degrees, 4 degrees, 4.5 degrees, go on 5, and we are finished. Perfect. And this other window has popped up. We're just going to go ahead and dock that. And this is for actually animating your modes. So if you were to, for example, hit animate, it would actually show you what your aircraft is doing. And in this state, if you read at the bottom, you'll see that we are trimmed at a speed of 7 meters per second with 8 per second angle of attack, and what all the flap moments are for what you need. And you can actually go through the different modes. So here we have, so this is our short response mode. This is a phugoid of some kind. A short response, another phugoid, and another short response. Well, in this case, it's this is probably spiral. Okay, very cool. So that's how you can animate these, and you have 2 sets of modes, either longitudinal or lateral, which are largely independent of each other, although all of them are a function of the, well, pretty much a function of where the CG is placed. So while this is very pretty, and it is somewhat useful for looking at the different trim states, let's have a look at the actual real engineering aspect of this, which happens in the loci plots or root locus plot. Now, this is actually not the typical case for it, because we have these things here, over here in the longitudinal part. These should not be here, but generally speaking, what you'll have is you'll have short period modes over here. In this case, these are all flat, so they damp out pretty much immediately. We'll have phugoids, which are over here, and then we shouldn't really have anything over here. This is going to resemble a spiral mode for longitudinal. And in the lateral modes, you'll generally find clusters. You'll find stuff over here which is roll damping. You're going to find stuff over here which is spiral modes, and you're going to find two things over here which will typically be Dutch roll modes. So, I'll preface this by saying that some stuff over on the positive side, as long as it's a small amount on the positive side, is nothing to be alarmed about, as long as it is on the axis and as long as you can identify its behavior as being a spiral mode. Now, what does a spiral mode look like in terms of animating it? This is generally what you would expect a spiral mode to be like. It's effectively just the plane leaving its flight path very gradually. So, for example, from a gust of wind or anything that induces side slip will typically, you can actually see it happening here, typically result in a loss of lift, which leads the aircraft nose to pitch down with a slight roll angle, which means that as it speeds up, it will start to pitch up again, and it basically starts to initiate a turn on like you would on a bank and yank aircraft, a two-channel aircraft, and it keeps doing this continuously. This process is continuous, and it basically forms a big spiral until either someone acts to correct this behavior, or you run out of altitude. So that's not something to worry about. And while it's an instability, the reason it isn't something to worry about is typically the time involved. So if you measure up this aircraft, we've really only moved about 1.5 meters in about 2-3 seconds. Considering a flight speed typically is going to be 10 to 12 meters per second. I mean, in this case it's only 7, but considering our flight speed, that's effectively we're talking about a very small amount of deviation from our flight path, and we haven't really lost altitude. In fact, in this case, we're actually gaining altitude more than anything else. So as long as these modes happen slowly, and as long as you have many seconds for a pilot to respond to your aircraft. In this case, this actually does look quite concerning, given the speed at which the aircraft pitches down. If we find a different one, so that's a phugoid. Okay, so in this case we have an instability. It's not a spiral mode. Looking at the way that it goes ahead and dies, that's definitely not a spiral mode. But again, there is 4 seconds for the pilot to understand that this is not an appropriate angle of attack for an aircraft, and to it's actually that way up. So you've got 4 seconds to understand that this is not, this is bad, and you should dampen this out. Obviously, this is not great. This would be a lot nicer if it was much closer to the origin. But again, in a pinch, that is something that you could warn the pilot about. Again, this is why these analyses are performed. This is looking a lot more like a spiral mode, where you have many seconds, and the aircraft does eventually fall off screen. That's fine. But again, you've got 4 or 5 seconds on your spiral mode to do something about it. Does it show me it does not show me the exact. Okay, so what we've got here, we've got roll damping. No, that's Dutch roll, isn't it? Yeah, that's Dutch roll. That's definitely Dutch roll, that walking around, and that's probably going to be a roll damping. Okay, so what are the criteria, and what do you really need to look for? Well, the thing to look for is anything up here in these clusters being in the positive part, so in this quadrant or this quadrant over here. Anything that's real is going to be unstable. Anything that is going to be between 0 and -1 is going to be what I would call marginally stable, i.e. I would not expect a timely response to the original flight conditions, but you could expect that a disturbance, for example, if a gust of wind under a wing induced a 15-degree bank angle, you would expect that bank angle to stay there for the time frame that is relevant to piloting this aircraft. And anything that is below -1 is going to be stable, so this stuff here is going to damp out relatively quickly. So if we look at, for example, mode 1, what we'll find is that this stuff within about a second and a bit has this disturbance of 1 meter per second has damped out completely, whereas let's have a look. Mode 2 is at -0.8. Okay, so this is right around that -1 sort of value. This stuff I would expect to not really damp out that quickly. Again, compared to a sub-second response, it's not terrible, but it's not bad either. And then you have this stuff that is at a plus value, and this stuff does not damp out. This stuff, you have about 4 seconds to catch it. After these 4 seconds, you find that things very quickly fall out of hand. I mean, within 4 seconds, yeah, we're talking quite big disturbances. So really, you've only got about degrees per second. Yeah, you've got, you know, a second or two to catch this sort of thing. That's definitely on the short side, but that's something that if you had a prototype aircraft that you were flying in a matter of hours, you could definitely brief the pilot about and be aware of. And the other thing to keep in mind is a gyro for something like this would be pretty much perfect. Obviously, if this happens within a second, a gyro is not, you know, these things operate at 30, 40 hertz. Last I looked in the RC space, for the old ones at least. They would not have enough iterations to really get the kind of control inputs you would need to prevent these sorts of catastrophic behaviors. But when it looks like this, you've got options. If it's sub 1 to 2 seconds, you have a critical design flaw. Do not fly the aircraft, because if you do, you'll be flying it once and you'll be picking up the pieces afterwards. And ideally, you'd want at least 10, 20 seconds before this really starts to get moving. In terms of reading up more on this, there are Wikipedia articles on aircraft on aircraft stability. There is most third-year aero students will cover this in some form, and there is also a PDF called Stability Analysis with XFLR5, which I will attempt to look up. Although I reckon stability analysis with XFLR5. We'll see if we find it. Okay, there is this beautiful PDF from the people, I think, yeah, from XFLR5, the people behind XFLR5s themselves, which actually goes on to a number of the fixes, and as well as what it all means there. I think there's also a great little plot somewhere that shows what to look for in, I think I saw it, here it is, that will show you exactly what to look for in terms of the typical root locus graph. So again, if you're doing a report and you want to double check that this is, that you have things the right way around, this is definitely something to have on hand. That's the main stuff. So in terms of how do we fix this aircraft, well, the first thing to keep in mind is our central gravity position. If I remove the surfaces, our central gravity, let's go ahead and look at this from the top. Which one's the top? There we go, from the top view. Damn it. Okay, from the top view. Our central gravity, the rule of thumb is around the quarter chord. In this case, we're about right. We probably could move, stand to move it a wee bit further forwards. We do seem to have some authority, but I think we can probably benefit from moving the tail back a wee bit. So let's go ahead and do this. Right, we're probably going to change our trim angle a tiny bit. No, we probably want a bit more nose down, if anything, so we'll get a bit of elevator angle on that. We will reduce our wing angle because we're quite light for the size of the wing, and we will basically try to move our battery a wee bit further forwards, and maybe add a turn our motors correspondingly. Okay, if we do all these changes, blah blah blah, yeah, we'll look for our changes. So our COGs should have moved forward just a smidge, and the other thing we really need to do is we're going to have a look from the side. You'll see that we put everything in the same plane. Now ideally we would go ahead and actually mount, if I remember that was Z-axis, and we need to go negative. If we were to mount everything 10 centimeters, not 10 meters, underneath the origin point of the wing, what we'll find is the traditional result that high wing aircraft are more stable. Hello. Can we go back? Do you mind? Has it moved? Oh, okay. I'm actually thinking I've got my Z and Y columns confused because I'm thick. So let's go ahead and move these down 10 centimeters. The centre of masses, and what we'll find is that actually moves our centre of gravity down the ways, and that's generally going to be quite good. So we've moved our empennage back, we've moved some of our mass lower down, and if we rerun our analysis, we actually need to redefine it. That's highly annoying. Control parameters, elevated tilt 1, yep. Let's go ahead and run this. Plus 5 is 0.5. Okay, so having a look at our root locus plots, we have actually made things worse. This is highly interesting, and I'm not even sure how we've ended up with two different sets of modes. What the heck? That one's fine. That one's fine. Touch roll, damping factor is negative. That would generally mean it's getting worse. That's getting worse. That's fine, that's fine, that's fine. Okay. So in this case, what we appeared to, we've got most of the modes are now more stable in the sense that the spiral mode is gone off of our longitudinal plot. Our lateral mode, our spiral, is actually quite stable now. So this is great. This is great news. If we look at this plus blah blah blah, yeah, that time is effectively 0. That's fine. Unfortunately, we do have an unstable mode here now. As to whether that's an anomaly from the relatively poor quality data and rather low number of panels I've got in here, I actually can't say. If we look at that mode, does it tell me which mode it is? It needs to be positive, and it's not that one. Positive, okay, it's this thing. It's 5 degrees 4. Mode 4 on lateral, so no, but if we animate this, what is this mode? Okay, it's a very interesting kind of spiral. Is it? Maybe. That's what the aircraft is doing. In this case, we do have plenty of time to act on it before it becomes a problem. If we just go ahead and have a look at that. Yeah, nothing huge. If I just rescale this, maybe that would maybe be useful. Graph scales. Yeah, this is a very interesting mode, quite complex, and I think what this comes down to in this case is we should not have done this. We should remove the tilt angle from the tail and then rerun our stability analysis, which we have to redefine. Again, highly annoying. I think it was 0, I think it's what we ran. I think it's what the ones that give us good, valid data, i.e. trying to pitch the nose up, which makes perfect sense considering that the centre of gravity is forwards of the quarter chord. We have a nose-heavy aircraft, and as the adage goes, nose-heavy aircraft fly badly, tail-heavy aircraft fly once. Now that done, we should have some somewhat cleaner plots. But generally, all these modes are stable in this window, so I'd be reasonably happy to build this aircraft, give it to someone, and warn them that it will fly like a pig, but that it should be more or less flyable. It's concerning that we do have these longitudinal modes that are barely stable. We may find in this case, if we have a look at this, it's stable. We have a phugoid. It does seem to take, if I just were to increase the time step and see what, come on, let me increase my time step, will you? There we go. 4 seconds, 5 seconds. Yeah, the spiral mode takes a while to really kick in, or whatever this mode is. That's not terrible. Yeah, okay, I would say that's kind of nose heavy more than anything else. So if we were to move our masses back a wee bit, let's go minus 0.12 on that. Okay, okay. COG. You know what? That's it's always hard to tell when you've got a tapered wing, because whether if the centre of gravity is on the quarter chord here, it's actually going to be much further forward than the quarter chord here, and it also depends how much lift is going on at every point. But anyway, I think that's enough rambling on about what we need to cover. The last thing we need to do is to have a look at exporting this data into a plot. With the stability analysis completed and the loci plots generated, the last step really for an engineer is to make some pretty pictures. This actually seems to have cleaned up very nicely. I think that was moving some of the masses back the ways so we don't have such a nose-heavy aircraft. So this is now much cleaner. I'd be much more happy giving this to a pilot. Anyway, we want to have a look and make some pretty plots. And generally, that would happen with log file. You can either go ahead and type this out. In older versions of XFLR, I did not find a good way of getting this data out. So what I will do is I will go ahead and save this as loci.log. With the log file saved out to loci.log in this case, what we can do is import the EIPass tool. So that is over at git.main.space. I think a copy exists of this project on GitHub, but the XFLR EIPass or eigenvalue parser is exactly what you're going to need. So if we just download the source, blah blah blah, I can match. Yep. We're going to extract this somewhere. The only tool you will need is the free Pascal compiler. From here, that is going to let you build this thing. And let's go ahead and load up this stuff here. Cool. Build.sh eipass.pascal file. There we go. And that should give us the eipass utility. Which has not found the file. Let me have a look and see how I'm supposed to use this. It's been ages since I haven't had to pick one of these plots. So it reads log.txt and it will create a lateral.csv and a longitudinal.csv as long as they're in the same directory. So we will go ahead and save our log.txt. So this needs to become log.txt. So we'll save that in the folder log.txt. And then we can go ahead and run this. EIPass. There we go. So that has successfully passed all the latitude, lateral, and longitudinal modes, and it should have generated a pair of CSV files. Here we are, longitudinal and lateral.csv. So if we then load up Octave, this is generally quite straightforward. Oh god, I haven't run Octave yet. Okay, very cool. Thank you. Edit. If we do lat equals dlm read lateral.csv and long equals dlm read longitudinal. Did I spell with an O or with an I? Actually, longitudinal has a typo in the code. Intentionally left for the reader, and then we just plot. Let's see what we get out of this actually. If I just run this, EI plot, avoid the classic mistake of making your MATLAB script called plot.m and then have it all break on you. If we go ahead and EI plot, dlm read, I'm able to find lateral. Okay, I've put it in the wrong place. Big brained. Oh, great, we need to close this, and then we need to move EI plot into here, and then restart Octave. Hallelujah. Can you tell this video was badly planned? No, that's not what I wanted. Oh my god, what am I doing? EIplot.m. If we run this, we have two variables which look like this. Now I'm very interested in what all this crap means. Okay, and it'll load up this matrix or this vector from the CSV file. Now what these columns mean, this is the flight speed at which trim was obtained, and then you have the real component and the imaginary component. It's actually a very simple program. It literally just outputs flight speed mode, real mode, imaginary, and that's it. And then it just looks for a very specific, well, it basically looks for very specific formatting within the log file. As you'll see, the eigenvectors and eigenvalues always look very specific within a very specific format. So that's all it does. And then once we have this, obviously we can just go ahead and plot, for example, our lateral stability by plotting every row second column against every row third column. And hallelujah, if we just remove and plot it with an O. There we go. Or it's stretch plot with an X then, because this is quite ugly. There we go. So now you have a plot that you can Format at your leisure, maybe your grids or whatever. You can include this in your reports, output this. It's a very similar process within MATLAB to load up a CSV file. So I think that is the end of this installment for XFLR and very basic stability analysis and what to check with regards to your aircraft. Thank you for watching.